Well, talking about pigeonhole principle, and the example that we already see is like the whole idea is that when the number of pigeons is more than the number of pigeonholes, we can say there exists at least one pigeonhole with more than one pigeon. In it. And well, it seems so obvious, but actually, as you know, in discrete math, what we have is that when we talk about something, we need to prove that. And what people like do most of the time to prove the problems which are dealing with pigeonhole principle, they say, okay, I divide the number of pigeons by the number of pigeonholes, and since the number is greater than 1, then I can say there must be something like some pigeonhole with more than one pigeon in it. And they call it direct proof. But it is not a good idea, and I don't recommend that at all, because in this way, it's like you are suggesting one way to distribute the pigeons into pigeonholes. It's like you say, okay, I distribute them in a uniform way, and like I divide that to have like exactly the same number in each of them. Also, what else is that is like, well, let's assume you have like 5 pigeons and 4 pigeonholes, and what happens is that what you say is that, okay, I divide that 5 over 4 is equal to 1.25, and it's like if they like uniformly go to the different pigeonholes, in each pigeonhole I will have 1.25 pigeon, which is not like, does not make sense to have like 1.25 pigeons. And it is the reason that I say direct proof is not a good idea to prove that. It's like you can guess the number, you can realize that, okay, this is more than this, so it's like there exists one pigeonhole with more than one pigeon in it, but it is not a good way to prove this idea. What I suggest to prove this idea is proof by contradiction. And proof by contradiction is actually, you remember, it's like we assume what we conclude is not correct. So we assume that there does not exist at least one pigeon, any pigeonhole with more than one pigeon in it. We assume that there does not exist any pigeonhole with more than one pigeon in it. Okay, what does it mean? There does not exist any pigeonhole with more than one pigeon in it, which means in each of the pigeonholes there is at most one pigeon. So in each pigeonhole there is at most one pigeon. And if we say that the number of pigeonholes is like n, we show that with n, it means that the number of pigeons, since in each pigeonhole there is one or no pigeon, it means that the number of pigeons is at most n, which means the number of pigeons is at most n. So the number of pigeons is equal or less than the number of pigeonholes. What we see is that it contradicts our first assumption that the number of pigeons is greater, strictly greater than the number of pigeonholes, which contradicts the assumption that number of pigeons is more than number of pigeonholes. And like basic questions, simple questions in this chapter is like, okay, we have like 13 people and we want to show that there exists at least one mouse with more than 2 people having birthday in that month. One person who has birthday in that month. And well, is like we want to show that, so it needs that proof. And what proof method we use is proof by contradiction, assuming that there are no 2 people with the same birth months, and if in each month there is at most 1 person, we must have at most 12 people, which is the contradiction. I don't write the whole thing because I think my explanation is enough. You can write it yourself. And what I'm going to talk about is the example 10. In the lecture notes. This example is also a Rosen textbook problem. And the problem says that let's assume we have n plus 1 numbers. And these numbers are all less than 2 times n. And well, what we want to show is there must be an integer that divides one of the other integers among these n plus 1 numbers. I'm going to write the whole problem here instead of just writing keywords. It's like show that among arbitrary n plus 1 positive integers, non exceeding 2 times n, there must be an integer that divides one of the other integer. Okay, so these numbers, these n plus 1 numbers are all positive integers and they are arbitrary numbers, so we cannot say that they are like consecutive or anything. We don't know if they are odd, they are even. We don't have any idea about those n+1 numbers. The only thing we know is that they're positive integers non-exceeding 2 times n. And what we want to show is that we show that there are 2 integers there such that one of them divide the other one. So what I want to do is that I want to show these numbers, these n+1 numbers with like a1, a2, a3 to an+1. We know that they are all less than 2n. Okay, for each of these a1, a2, or I can like say ai, such that I is like between 1 and n+1. It is like showing the index. I want to write these numbers in the form of 2 to the power of some number times an odd integer. Let's see what it means. Okay, what I said was, well, again, I write that we have the sequence of a1 to an+1. We know that they are less than or equal to 2 times n. And since they are like positive integers, they are greater than 0 as well. So what I want to do is that I write each of these numbers, like ai, as 2 to the power of some power, like 2 to the power of ki times qi, such that qi is an odd integer. Let's see what it means. It means when I have something like 5, number 5, I can write it as 2 to the power of 0, which is like 1, times odd factor of that, which is 5. Or let's say for each of these numbers, I'm writing them as the even factor, like 2 factor times the odd factor. So if I have any odd number here like 5, we know that the odd numbers don't have any factor of 2. So the power of 2 that we are going to use is for sure 0. So if you see any other odd number like 11, you can immediately say that, okay, the power of 2 must be 0 because odd numbers don't have any factor of 2. And since it is odd itself, I can use that as the odd factor. What happens in even numbers? Let's say, for example, for 6 is 2 to the power of 1 times 3. The power of 2, which is 1 here, times the odd factor. And for some number like 8, which is a power of 2 itself, I can rewrite as 2 to the power of 3 times 1, which is like odd factor times the 2 to the power of some number, like power of 2. So what I have is that it is like even or 2 factor, not even, because it's like 6 itself is even, so it is better to say that factor of 2 or power of 2. And here is that odd factor. So let's say for each of these numbers I do that. So first I had like a1, a2 to an+1. Now I change that to 2 to the power of k1 times q1, 2 to the power of k2 times q2, 2 to the power of kn times qn, and 2 to the power of k with index n+1 times qn+1. We have this. Now let's ignore the part of like powers of 2, and I only write the q's, like q1, q2 to qn+1. What I know about them, see, all the ai's are less than equal to 2n, and 2n is an even number itself. So there is no chance for these to be 2n, so they must be less than 2n. And they are greater than 0. Now the question is that how many of these numbers, or not how many of these numbers because they are all odd, how many of numbers in this interval between 0 and 2n are odd? How many, let's say, different odd numbers exists between 0 and 2n, 2 times n. And you know, well, numbers are like even, odd, even, odd, even, odd, so half of them are odd, so n different odd numbers. But how many odd numbers do I have here? They are all odd, right? That Q part are all odd. So there are like n plus 1 odd numbers. Okay, what does it mean? We only have n different odd numbers, and here we have n plus 1 odd numbers in that interval, which means that at least two of these numbers, two of these like QIs must be exactly the same. It's like they are like n plus 1 pigeons instead of n plus 1 odd numbers that are exactly like n plus 1 pigeons. And these n different odd numbers are like n pigeonholes. And what I can say is that there exist two indices, like let's say J and H, such that QJ is equal to QH. How can I say that? Based on Pigeonhole Principle. Okay, now what I can say is that, well, I know QJ is equal to QH, but that QJ is the odd part of AJ and QH is the odd part of AH. So rewriting that AJ, it was 2 to the power of KJ times QJ, and AH is equal to 2 to the power of KH times QH. So let's see, we know these parts are equal and we have two numbers. Well, we can say one of them is greater or equal to the other one, and without loss of generality, I can assume AJ is greater or equal AH. It can be like the other way, but anyway, one of these is greater or equal to the other one. So let's assume AJ is greater or equal to AH. These parts of these two numbers are exactly the same, the odd factors. And this 2 factor of these, since it is greater than the other one, so the 2 factor of J must be greater than the other one. So 2 to the power of KJ is greater than 2 to the power of KH. And since they are like both are the same bases, I can say KJ is greater or equal KH. Since it is greater or equal to this, I can say, okay, KJ is equal to KH plus something. That something can be 0 if they are exactly the same, and it can be a positive number if KJ is greater. So I can say there exists T greater or equal 0 such that KJ is equal to KH plus T. Well, now let's divide AJ by AH and see what happens. AJ is equal to 2 to the power of KJ times QJ. AH is 2 to the power of KH times QH. And since these two are exactly the same, I can cancel out them. And instead of, well, I can say 2 to the power of KJ over 2 to the power of KH. And instead of KJ, I can write KH plus T. So it is 2 to the power of KH plus T in the power both over 2 to the power of KH. And well, you know, it is equal to 2 to the power of KH times 2 to the power of T over 2 to the power of KH. which is equal to 2 to the power of t. And since t is greater or equal to 0, I can say since t is greater or equal to 0, 2 to the power of t is greater or equal to 1, and it is an integer. So since t is integer, let's say z. I can also use natural numbers. And since it is like this, I can say aj divides ah, and we are done with the proof. Okay, having all this, now I'm going to talk about the generalized pigeonhole principle. Okay, when we have a number of pigeons is greater than number of pigeonholes, we had that conclusion that, well, there exists at least one pigeonhole with more than one pigeon. But what if there are like more than like many pigeons and a few number of pigeonholes? What can I say in that case? I still can say there exists a pigeonhole which has one or more, actually more than one pigeon in that. But can I say something stronger? Let's assume what happens if I have 11 pigeons and 2 pigeonholes. See, any way I distribute these 11 pigeons into 2 pigeonholes, there is at least one of these pigeonholes with at least 6 pigeons in that. Or more than 5. I can say more than 5, or at least 6 pigeons. Well, to find that number, not for a proof, but to find that number, you can divide that 11 by 2 and find the ceiling, which is equal to 6. So you can say it is at least 6. If you just divide that by 2, it will be something like 5. I mean, the integer part is 5, so you can say more than 5. Here, you must say at least 6. Okay, here's the whole idea with that simple example. I'm not going to write the whole proof, just giving the idea, but I'm going to write the generalized pigeonhole principle, which is theorem 12 in the lecture notes. And I'm not only writing that theorem, but also I'm going to prove that, write a proof for that. So what generalized pigeonhole principle says, the theorem, is that if n objects, which is actually pigeons, are placed into k boxes, then there is at least one box with at least the ceiling of n over k objects. Okay, first talking about the ceiling function, it's like when you have a number like 2 and it's just integer, it maps it to the same number, so it doesn't have like any part after like point or something. But when you have like 2.3, it changes to 3. If you have 3.4, it changes to 4. Like 3.6, it will be 4. So you see, if it is greater than this number, it is going to be the first integer which is greater than this number. So you see, it is greater than this number less than 1 unit. So it never happens that it is exactly 1 unit or more. Well, so it is the ceiling, and I'm going to use that idea in the proof of that. Well, you know, the suggested way, not the suggested way, actually the correct way to prove this theorem is proof by contradiction. In proof by contradiction, we assume our conclusion is not correct, so we assume that there does not any, assume there is no box with at least this number of objects, which means that all the boxes have less than this number objects in them. So all boxes contain at most n over k, the ceiling, minus 1 objects. Okay, now let's count the number of objects, which means there are at most, see, in each box I have at most this number of objects, or less than, at most means that this number or less than this, and we have exactly k boxes. So the number of objects in total will be less than, or not less than, less than or equal to k times n over k minus 1, the ceiling, minus 1. Okay, what can I say about this number? See, what I know is that the ceiling of n over k is less than n over k plus 1. The floor or integer part, I also can use this. In the case that it is integer, they're exactly the same, and this remains. So in total, I can say the ceiling n over k is less than n over k plus 1. Okay, what happens here? It's like k times n over k minus 1 is less than k times n over k plus 1 minus 1, which is, I'm writing here because I don't want to go to the next page, k times n over k, which is exactly equal to n. Okay, see, this number is less than n. It means that there are at most this number of objects that which means there are at most this number of objects. Okay, the greatest possible number of objects is less than n, but we know that there are n objects, so it is the contradiction. I'm going to write that as well. Since there are k times n over k, ceiling minus 1 objects, at most this number of objects, which is less than n, we have a contradiction with the assumption that there are n objects. So the assumption that there are at most n over k minus 1 objects in each box is not correct. Okay, we proved the theorem. I'm going to show one example. In that example, I'm going to use the idea of generalized pigeonhole principle. The example is example 13 in the lecture note. It is also one example. The example is also in Rosen textbook. And the example says in a group of 6 people, each pair between any 2 people, each pair either likes each other or hates each other. And what the problem is asking us to prove is that prove that this group contains a 3 subset of people who mutually like each other or who mutually hate each other. Okay, so it's like if I show people with like dots and the relationships with these lines, like hate with green and like with red, at the end I want to see if there is like any red triangle or green triangle, and the problem is asking me to prove that there exists at least one of these, like a triangle that there is like each pair has that like relationship or that hate relationship. Let's see how we can prove that using the idea of generalized pigeonhole principle. Okay, so as I said, let's assume I show each person with 1 dot and I name them, okay, person 1, person 2, 3, 4, 5, and 6. And let's talk about this guy, person 1. What can I say about him or her? Say there are 5 other people here, and P1 has either hate or like relationship between any of these, between him or her and any of these guys. So we have 5 people, 5 other people, but there are 2 kinds of relationship. Like hate or like. Since there are 5 and there are 2, based on pigeonhole principle, generalized pigeonhole principle says that P1 has the same kind of relationship with at least 3 of these people. Okay, so we don't care if that relationship is actually like or hate. So let's assume that he or she has a like relationship with 3 people without loss of generality. If it is hate, it is like just green. The difference is that it is green. And these 3 people can be any of these 3, but I just, for making it simple, I choose these three guys and say, okay, let's assume P1 has the same relationship with these three. If there are other three people, it will be the same thing, just different indices. So I can do that. It is not making it like simple or suggesting a solution. It is general. The only thing is that for sure we have this pattern. The only thing is that maybe we have different indices here. Okay, so what I see is that P1 has like relationship with these three people, or the same relationship with these three people. Okay, now do you agree that if P5 and P6 have like relationship, I have that red triangle, I have that three subset that all people like each other, like between any two, there is a like relationship. Well, so if I color, if it is like, we are done. Also, if it is like, I have that triangle, we are done. Also, if it is red, I have that red triangle and we are done. So if any of these are red, we are done. And actually, we proved that. So let's assume that none of these are like relationships. If none of these are like relationships, there must all be hate relationships. If they are hate relationship, what I have is that triangle in green, which is a hate relationship triangle or three subset with all hate, like they mutually hate each other. Okay, so I just showed the proof with that like model and use the generalized pigeonhole principle to realize that P1 with at least three of these guys have the same relationship, and then we showed that since there are like three of these, if any of these two guys have like relationship, I will have that three subset like relationship, and if not, I will have that green or hate relationship. You can read the solution in the lecture notes. I'm not going to write the whole thing. But if you think that is confusing or it doesn't make sense, you can ask questions during office hours. And well, talking about, actually we are done with pigeonhole principle. Now let's talk about permutations. And after permutation, or actually part of permutations, I'm going to talk about derangements as well. Maybe we talk about this topic in the next lecture, Wednesday's lecture. But now I'm going to talk about permutation. Well, let's assume that I have like three numbers, 1, 2, 3. But when I have these three numbers, I write it like as 1, 2, 3. I can rewrite that like as some other way, like 2, 1, 3. And it is different than this. Like it is like I have the same numbers, but different orders give me a different way. Is like there are three people, and well, people are always different, and I'm asking them to stand in a row to take a picture. And well, one way is that these three guys stand like this or like this. Like this. There are different ways to ask them to stand in that row, right? Like these numbers. Like it's like I have 1, 2, 3, and then another order is like 2, 1, 3. It's possible that I write it as 3, 1, 2, and many other ways. But like many other ways, what does it mean? What is the exact number for that many other ways? It's like, okay, let's say I have that first place, second place, third place. It is possible that I have any of these three guys to stand in the first place. So there are three ways to have someone here. But now that someone is standing here, one of these three guys, I only have two people to ask to stand here. So I have two choices to fill this place. And then I have one, because there is only one person, to go to the last place. It is 6, or as you say, 3, 2, 1. It reminds you of 3 factorial. So what happens if I have n people? You see, for the first place, I have n choices. Any of n people can go here. Then after fixing this, there are n minus 1 people can go to the next one. And n minus 2. And the last place, there is only one person to be here, which is equal to n factorial. So there are n factorial different ways to ask n people to stand that line. And it is the number of n permutations, or number of permutations, of the set 1, 2 to n. I use another notation to show this set. When we use this, it is the same as writing the set 1, 2, 3 to n. So if I write this with 3, it will be 1, 2, 3. Okay. The next example is also a really easy example that I want to talk about. It's like, now assume that we have the 4 numbers and we want to see like 1, 2, 3, 4, or set of 4. And you know the number of permutations of these 4 numbers is 4 factorial, which is equal to 24. But what if I have these 4 people, but I want to ask 3 of them to stand in a row? 3 places, but 4 people. Okay, for the first I have 4 choices, for the second I have 3 choices, and for this one I have 2 choices. You see, I don't have any last place. Or what happens if I have 4 people with 2 places? I want to have only 2 of them. It's like 4 people apply for a job, and like there are 2 different roles, role 1 and role 2. See, these 2 roles must be different. They are not exactly the same. We will see why I say they are different. So for role 1, I have 4 choices, and for role 2, I have 3 choices because one of them is already hired for role 1. So you see it is 4 times 3, and it's 4 times 3 times 2. Okay, we call these R permutations, like 2 permutation of set 4, and it is like 3 permutation of the set 4. And can we find a formula for that? See, here it's like I have n times n minus 1 times, I go until I reach the point n minus r plus 1, right? Because there are r places, and this number is the last one to have that. The number of people who are left to be in the place r. You see why, for example, if I have 5 people and 2 places, it is like 5 and 4, because after these 2 I'm done. So here I'm going to just put r numbers, n minus 1, to n minus r plus 1. See, if I have n to n minus r, it's like, if it is the first one, like it is, I'm subtracting that n minus r numbers. If I do the same here, it will be r, right? Sorry, it is like 0 and it is r. So what you see is that here I have r plus 1 numbers. So it is the reason the last one is not n minus r, it is one more than that, n minus r plus 1. It is the formula for r permutation of the set of n. And maybe we can write it better. See, if I had that as factorial, what part was missed? It was like n minus r times n minus r minus 1 times the rest until 1, right? If I had this part, it was n factorial. So it seems that I have the whole thing for having n factorial, but I need to divide that by this. So it is like I am multiplying this to this fraction. You see it is 1, so it is not changing anything. But the result is n factorial over n minus r factorial. So here is that formula. We need to do that to show the formula. So r permutation of n can be computed by this formula or this formula. Both of them are the same. And we have this problem. Okay, now asking one other question. Let's assume that you want to create a password for one of your accounts, and it's like asking you to have a 4-digit password, like it is a PIN code or something. And well, it means that you have 4 places, 4 digits, and the digit can be any number between 0 and 9, and for each of these places you can use any of those. So how many choices do you have here? 10 choices. Again, 10 choices here. 10 choices for the 3rd place. And 10 choices for the last place, which is 10 to the power of 4. See, this one is not a permutation because we don't have those objects to reorder them. It's like for each of them, I have different ways to have any of those 10, and then I can use the same number for the 2nd place, for the 3rd place, for the 4th place. But when you have like 4 people, you are asking them to stand in a row. It's like you cannot ask the first person or one of the people to be in the 1st place and 2nd place and 3rd place, because when he or she stands in one place, then it is not possible to ask him or her to go to the other place as well. Okay, so here it is not a permutation, it is a product rule. I talked about that before in the class, but I just wanted to show the difference that here we have like repeats. But let's see, if I have like 4-digit password with no repeat, such that all digits are different, in this case, I have those 4 places, so I have 10 digits for the 1st place, but since I used one of these here, I'm not allowed to use the same thing here. So I have 9 choices here. And then I've used 2 digits. I have 8 choices here, and I have 7 choices here. See, here it is like I have sets of 0 to 9. And I'm going to find 4 permutations. So since they are like 10 different numbers, it is like 10 factorial over, or n factorial over n minus r factorial, which is 10 factorial over 10 minus 4, 6 factorial, which is the same as 10 times 9 times 8 times 7. Okay, next time I'm going to give more examples on permutations. We are also going to talk about derangements and sing 1 or 2 examples on that. And after those, we are going to talk about combinations. Thank you, and we'll see you next time, Wednesday.